Someone just mentioned a lecture on Sunday night and the gondolas in the mountains, so something a bit crazy is going on. So I'll try to continue in this direction. And so there are some people mentioned here that we greatly benefited in interaction with, and some of these are co-authors of the papers I will mention. Others are just been very important to understand a lot of open problems. So, of course, one of the things laymen accuse scientists of is doing scientific tourism. So let's try to follow the stereotypes, and it's important. So I want to, before I start, of course, it's the opposite. Scientific events are really important aspect of scientific growth and exchange of ideas. I just want to mention a few things that are happening that were somehow directly involved with the new Center for the Mathematics of Planet Earth and at the University of Reading. So just now there's going to be a conference called ClimateNet, and it's very late, but if you have any ideas, you want to participate and submit an abstract, there is still availability. Next year, the rest are actually recent news. There's going to be a workshop on non-equilibrium system at ICTP with topics including also geosciences. In 2 years, almost 2 years, in the week selected for the best climatology of snow, clearly, we're going to have a workshop on themes related to what is being discussed here. And the autumn of next year, there's going to be another, this is a 3-month program at the Poincaré Institute on the mathematics of climate and of the environment. So if you're interested, just let me know. So now, after this advertisement, let's go to the presentation. So let's start from what inspired me to look into this melancholia state and why I call them so. So it was a very dark afternoon of 2011, and I just moved to Hamburg. It was late. I have had a very long meeting with my colleagues, and my wife said, we have to go to see the last movie of Lars von Trier. And the movie starts like this. And it's a masterpiece, actually, this movie. And I said, okay, after 7 hours of meeting with my colleagues at CLISUP, that really makes sense. And then I watched the movie. And the movie is really an incredible movie because it talks, I think it's an incredibly accurate representation of the main issue related to tipping points, which is not the catastrophic event, which is in fact at the beginning, to remove the tension from the audience, is the lack of predictability near the tipping point. So this is the essential element, and that's actually what inspired me in this work, and that's what we got at the end after 6 years of work. And if you watch the movie, which I encourage you, you will see what I mean. So, but now let's try to put the concept in a broader range of topics. So, the main problem, one of the main problems we face in natural and mathematical sciences is understanding the response of a system in very general terms to perturbations. And of course, we deal with issues like robustness, whether we can do a smooth response analysis of the system, and whether we go into the critical transitions. And there is a link in this properties that we will see. The starting point for most of this, at least in the context of statistical physics, comes from the work of Kubo in the late 50s, who established formulas to predict the response of a system near equilibrium, as described by the canonical ensemble, to perturbation. And this is the basic of most of our results we have in acoustics, optics, condensate matter, and so on. And the main cornerstone of all the theory is the fluctuation dissipation theorem, which gives a dictionary allowing us to translate forced fluctuations and free fluctuation. That's a really important result. And there are some issues, though, that there's been a lot of criticism because the result was not physically rigorous nor mathematically rigorous, but it worked, which is interesting. And the problem is that the theory, as it is, works only near equilibrium. But so we go fast forward in time by 40 years, and in the 90s, Ruel showed that it's possible to construct a regular response theory of the form of Kubo's, if we consider special dynamical systems, which are called axiom A. These are systems which are uniformly hyperbolic on the attractors. Uh, the, what he also showed is that if I am in a non-equilibrium deterministic system, the fluctuation dissipation theorem does not apply, and there is a fundamental difference between the properties of the flow in the unstable direction, which is the direction along which the trajectory diverge, and the stable direction, which are those along which the trajectory converge. And one can start to see critical transition as a loss of smoothness in the response. Now, later the result have been mathematically improved substantially by some colleagues, Lucarini, Baladi, Dolgopiat, to more general case systems. Something I need to say is that these systems, which are quite special mathematically, are considered to be of general physical relevance because there is an idea, which is called the chaotic hypothesis, saying that if I have a system which has a lot of unstable direction, even if it is not uniformly hyperbolic on the attractor, it will behave at all practical level as if it were so. So these results are relevant, as we will see, for many practical cases. This is, as I said, the smooth part of the response, and then we go into the towards critical transitions. So remember, we have to link loss of smoothness in the response to this. And then when we look at critical transition, some keywords here. So one important keyword is catastrophe theory. This was in the 60s seen as the ultimate theory of nature, basically, structural theory of nature. And basically there is a global classifications of bifurcations in relatively simple system. Note that this comes well before, or around the time chaos is born as idea. Still the world was mostly considered as something which is equilibrium and perturbation around that. Now, very recently, in a very interesting paper, Peter Auschwin and others introduced the concept, generalized the concept of bifurcation from the usual bifurcations due to change in the parameter of the system to bifurcation that depend explicitly on the rate at which a parameter has changed and on the finite amplitude of a noise introduced. So that's a really important result. And another thing I want to say is that we have a very, very powerful theory, Friedlin-Wenzel theory in the 70s, and Freddy is very expert in these things, much more than me. And the idea is that this theory gives us general laws for understanding the probability of transition between two separate attractors. Induced by adding noise on top of deterministic dynamics. So we clearly see this is an important element of what we want to talk about. So now, why studying climate? What is the relevance of climate? Of course, it's enormous scientifically in the sense that it's really an amazing example of a non-equilibrium system, and we will see in a second more specifically what we mean. We have huge variability on huge range of spatial and temporal scales, and interestingly, the problem of understanding climate response to force and climate variability touches three essential aspects of science. So one, of course, what we're studying, many people are studying, the anthropogenic climate change. And if we look a bit back in the past, the relationship between paleoclimate and life, and instead if you look a bit away in space, the relationship between habitability and the conditions on different planets, which is one of the big topics around. And remember that in the case of climate, we have all the regimes of response. So we have smooth response and no smooth response. So what we mean by non-equilibrium, this is a very important thing. So not the system, so this is a very important. When one says that the equilibrium condition for climate, this is it's a wrong terminology. Climate is a non-equilibrium system, and it's forced fundamentally by lack of homogeneity in the absorption of solar radiation. So we have preferential absorption of solar radiation at surface than aloft, and preferential absorption of solar radiation in Goa than in Hamburg. Okay? That's very important. So what is the very complex dynamic we observe of climate is a way the system tries to adjust to these forcings and reaches eventually a steady state, what is called a non-equilibrium steady state. So vertical fluxes due to convection, in particular, exchanges in general across the boundary layer, as well as radiative exchanges, counter this vertical lack of absorption, and large-scale transport does the same for the meridional transports, and one can treat the problem in terms, as an example, of entropy production and so on. It's a very interesting area. So the climate can be seen also on a macroscopic level as an engine, a very non-ideal engine that generates work. Someone just mentioned the Lorentz energy cycle, basically through a conversion of available potential into kinetic energy with a certain efficiency. This is accompanied by a lot of reversible process, irreversible heat transport, and at the end, dissipation. Okay? And as we said, and this is the last qualitative things I will say, we have, in the case of climate, a co-presence. So climate is neither just turbulence, nor just features, nor just waves. It's a difficult, complex mishmash of all of this. So we have a variability on many scales, but on certain range of scale, we can characterize objects that for which we can find a sort of Linnaean classification. So all cyclones are different, but there is a concept like cyclones. It's not just something strange. Okay? So there is special balances taking place on special scales. So in this paper, we made a summary a few years ago of some of these issues. So now let's start. And the main point of the presentation is C, but in order to give you a sense of the context, I will have to go through A and B. So as I said, the response of the system, of climate system to perturbation, is a smooth regime of response. There is a region where we have high sensitivity to the response. And then we are in the region, there is a third regime where we have critical transitions. So when one planet hits the other, and there is not much to discuss, okay? Not much time for negotiation. You know, some negotiation, complex negotiation, soft Brexit, hard Brexit, just whatever. Okay, so okay. Yeah, but I have to say no workers' rights have been compromised in the production of the scientific work here, okay? So now, in this first paper that pertains to topic A, smooth response, with one of the co-authors is here, we basically showed how using the response theory for non-equilibrium statistical mechanical system, one can predict in an ensemble sense the response of the climate system to forcing using a simple but yet a GCM. Okay, so the first message is that the climate statistical mechanics allowed us to do this response. Something happened? Yeah. Okay. Good. So what is the idea? The idea is relatively simple. In the practice is actually simple. The difficult part is to prove this thing makes sense. So if I have what one can do is that basically if you have to take a background state, add a perturbation, and the response theory in general, and in particular in this case, the formal one developed by Ruel, allow us to express the change in the expectation value of any observable of the system as a function of the property of the unperturbed state. Okay, so that's the essential property of a response theory. Very interestingly, this can be done also when we have a time-dependent forcing. So in that case, we will have that the properties of my system will change in time. In other terms, for those of you who know the literature, one can reconstruct the so-called pullback attractor, so the time-dependent measure supported on which the time-dependent measure on which the attractor of this time-dependent system is supported. Now, what is what I want to say, the essential thing is that we are able to express the change in the expectation value of a parameter, so my climate response, in terms of the convolution of a green function, which contains all the physics of the problem, the background, what is the observable we study, what is the perturbation we do, and what is the invariant measure of my system, so what is my system, convoluted with this time-dependent perturbation. This thing is giving me some headaches. Okay, that's so the essential thing is that if I'm able to construct this green function, I'm able to do prediction. So that's a classic problem, and it's possible to do it also in this context. So we chose this model, PLASM. It's a simple model with about 10 to the 5 degrees of freedom, which includes a primitive equation model for the atmosphere, basically diffusive ocean. Please.
Sorry, would you go back just a slide?
Of course, even 2 if you want.
Would you mind explaining what's going into that Green's function, what those variables are? Theta, gradient of x.
Yes, you want to.
I mean, just a rough.
Yes.
I mean, qualitative.
Yeah, sure. Of course. So basically, the green function describes, as I said, it's indexed by the observable, okay? So this is an expectation value over the unperturbed measure. Rho 0 dx is the invariant measure of x dot equal f of x. Of the scalar, it's a causal function, so there is a nice theta in front of it. That's an essential requirement for any response theory, in fact. And it's a scalar product of my perturbation vector flow with the evolved value at time t of my observable. So this basically describes the impact at time t of the perturbation that has occurred as a result of applying with respect to the background state due to the presence of this X field. Okay? And yeah, I mean, there could be a lot of things to talk about, but thanks for asking. So now, anyway, the idea is how I can I construct this green function, and if so, how can I use it? I mean, the easiest way to do it is to do it actually in a very simple and experimental way. So what one does basically, just to rapidly, you know, just to translate it into climate, we take as observable the globally average surface temperature, we take as forcing the increase in the CO2 concentration, and the theory tells us that we can write an equation like this. The question is, of course, how do I estimate this? Because it's a mess. I'm talking about, do you feel comfortable in constructing the scalar product in 10 to the 5 dimensions with something that is evolved in time, reintegrating over the whole invariant measure, jumping and you know, singing in old Armenian? No, it's not easy. So you can, instead of doing a brutal direct approach, you can construct it by using linearity. So you use a probe forcing, you construct the green function from a probe forcing, and then you use it to predict the response to a different forcing. If it works, that means you have constructed the right green function. That's a classical procedure as an example in optics. So the idea is constructing this linear operator and then predicting the response. So basically what we showed is that this thing works well for a prediction of the globally average surface temperature, and I will go rapidly. I'm happy to talk about this in other contexts. You can define rigorously things like the so-called equilibrium climate sensitivity in terms of the spectral properties of the Fourier transform of this green function, which is called the susceptibility, and then you are able to construct in a very systematic way, you actually have a formula for deriving the so-called transient climate response, which was introduced by, as an example, Mycelian at the beginning in 2003, I think. So the idea is, assume I do a ramp of CO2 increase, and at the end of the ramp of CO2 increase, I will be able to, I will still have, I will not have reached the asymptotic level of temperature change because the system has some thermal inertia, and you're able here to construct a thermal inertia for any time scale. So you start to have, the idea is that instead of predicting one scenario, you're able to predict a continuum of scenario of forcing, and you can combine scenarios of forcing. So this is a way to study climate change. In fact, it's not only limited to global indicators, but you can use it also at local scale, as an example, zonal temperature averages, or even local temperatures. Because the idea, so the concept is that climate change in an ensemble sense can be predicted using statistical mechanics. There are many other things to talk about, but I will stop here. The next thing that is quite relevant is, of course, again, also we try not to kill too many spherical cows, and we are spherical vegetarian, and the idea is a concept that is typically taken is that force fluctuation will project on free fluctuations. This statement is false. The problem is, in non-equilibrium system, there is an essential difference between the force fluctuations and the free fluctuations, related to the fact that certain regions of the phase space are never explored by the system naturally, and certain directions are not, whereas forced fluctuation might lead us there. So, and the thing is that anyway, the non-equivalence between these two says that implies that the fluctuation dissipation theorem will not in general work. It might work for certain observables and certain forcings very well, but the theory says that there is a term in the construction of the response theory which will not be cannot be represented in terms of a fluctuation dissipation result. Things are different if I have stochastic noise, in which case instead the fluctuation dissipation theorem will work. Okay, that's a separate condition. And if you take, there's been a good and very good literature where people have tried to use the fluctuation dissipation theorem to predict the response of the system. And in some cases, things work very well. In some cases, things don't work well. So, yes? Yeah, I mean, like the climate has its own variability, right? So that's what I mean in this case. So it's in general, if I have a chaotic dynamical system, I have variability, its own variability, without introducing any forcing. So the difference between the presence of this variability is something that in some cases, if you are near equilibrium or if you have noise on the background, allows you to reconstruct the properties of the response of the system for basically any forcing. Okay? No, because it's not the main topic of here. I'm just giving some concept. Who knows what is fluctuation dissipation theorem? Yeah, a minority. So the fluctuation dissipation theorem tells, as I was telling before, allows us to do the following. I observe, let make it in a practical sense. I have a long run of a model or a long observation. Let's take it in model sense. I observe, I collect data on the model for very long, for a very long time, and then I construct correlation properties between suitably defined observable of this system. That's one side. On the other side of the blackboard, there is someone who writes me formulas, and these formulas allows me to relate such correlations to the green function that predict the response of the system to certain perturbations. Then the left side and the right side of the blackboard come together, and so with this data, I can predict the response of the system to perturbation. So that's the essence of the fluctuation dissipation theorem. So this is why it's extremely powerful and it's extremely important. But the condition under which it applies is that it is possible to use this data to do this prediction. Okay, so that's essentially the element. If I am in an equilibrium system, I can do that, and you can prove this, and I can basically, I do not need to do a forced experiment to predict the response of a system to perturbation. In this, you can conceptualize this as that forced fluctuations and free fluctuations are related, always. In a system which is outside of equilibrium and lives in an attractor or lower dimension, this is not always the case. So observing the unforced fluctuation of the system does not allow me to predict the response to all forcings. So I can have surprises. And now I will give you an example of a surprise. Okay? Thanks, Fred. Is it a bit clearer? Okay, good. At least it sounded so. Okay. So what we did in this paper here, and this is where is the following. So we took a simple model of the mid-latitude atmosphere. So this is a simple barotropic model of the atmosphere, force and dissipative. It's a system with only 200 about degrees of freedom and a very, let's say, it's a system with very high chaos relatively to its size. And what we found is that we studied the response of the system to various forcings, orographic forcing, diffusion, rotation. And we found, as an example, that if I change the orography of my system, I can do all the procedure I've told you before, and I discover that my system has a response that cannot at all be described with the fluctuation dissipation theorem. What I find is that the forcing of my system project in the stable direction of the flow, and it pushes the system in areas of the phase space that are never visited by the system in its natural variability. So what we'll expect? Expect that I will see phenomenology, climatic phenomenology, that I have never observed before. So that's what I called climatic surprise. There is something even stranger. I am pushing the system in directions. So in a chaotic system, there are so-called islands of regularity, which are not really regular, as the so-called unstable periodic orbits. So these are closed orbits in very high dimension that basically are very unstable. If they were stable, the system would not be chaotic. So this forcing pushes the system in a close resonance with some of these orbits. These orbits live in the very, very, I would say, outside range of the attractor. They are never populated by, if you look at the natural variability. But this forcing pushes the orbit around these unstable periodic orbits. The result is that I get a very regular behavior in the form of large-scale waves that are never observed in the natural unperturbed variability of the system. So this is a case where if I force the system, I will observe some large-scale object, very regular even. It's a slowly decaying wave that is unprecedented. So in other terms, one has to keep the eyes open to understand that it is not true that the problem of climate change is just a problem of changing a bit the weight of different climate modes in the unperturbed case. There can be new things happening, and there are mathematical mechanisms to explain those. Now, now we go towards the tipping points. So you start to see that there are cases where the response gives me some strange stuff. And now we will go into the direction of the very strange stuff, okay? So tipping points, the concept of tipping points is per se not new. It has to do with the critical transition, but it was made very popular and it became really central in a series of papers. This is a paper by Tim Lenton, 2007, where people described regions of the planet where climate change could lead to irreversible changes in the properties of the system. And big literature opened up from that, and we will look into that. So now that's thing. But let's see what it is. This. So let's look at these two scenarios, which I stole the picture from Tim Lenton, and I don't know from where, but whatever. So this is I have a parameter and I have something I observe. Okay. Okay. This is a case where I have a very high sensitivity. So if I'm here, I push a bit, and then things go down. And but if I go back, I will end up again here. But if I am beyond the bifurcation, I am in this scenario. I fight with my partner, I fight a lot with my partner, I fight a lot with my partner. Then I reach the breaking point, and you go into the ground state of being single, and you continue to fight. If you then improve your relationship, you're not easily gonna go back to the previous state. That's why they call it a breaking point. Okay, so how can we treat this problem? And this cheap psychology, actually, the idea is I have a one-dimensional ordinary differential equation describing the dynamics of a variable, and I have some noise. So in this case, I can bring the problem to a problem discussed in terms of an effective potential, and being in this scenario here means that in a certain parametric range, I have an effective potential which has two local minima. So basically, what is the idea? I am here, my noise makes me stay here, and after a while, I jump to this state, and then back here. That's called the Tinder in modern day world, okay? And you do this, okay? Now, if I change the parameters of my system, this one, I could go to a regime where one of these two minima is deeper or not, and then I can get to a region where one of the two becomes flat, and I make a transition to just a monostable system. Now, in general, if the system behaves like this, we have a relationship between the probability and transition and the intensity of the noise. And the problem is that if you give me a time series where the PDF has a two maxima, I can always construct a dynamics that looks like this. But beware, this is not a robust procedure, because I can have a very high dimensional system which produces me a bistable dynamics, but the dynamics is not written only in the coordinate of the observable I see. Okay? So there is a problem of projection there that makes the procedure not robust in general. Now, okay, now let's get to the region where we are here. Okay? And then we will go to here to the actual transition to this state. So now, in two papers we have written, the first author is Alexis Tanté, is very, very talented young guy. We studied this problem of nearing the transition using the so-called transfer operator formalism that allows us to study how the ensembles of trajectory are pushed forward by the dynamics. One constructs an operator describing this and studies the spectral properties of this operator. That's the second paper. So what happens, and this I will just mention, that near critical transition there are two phenomena that one can prove mathematically happen. One is the so-called critical slowing down. Near a critical transition, the system will start to oscillate very slowly, the variability will become very slow, the memory will become very long, and then as a result, the response to perturbation will diverge, basically because the system will not decorrelate. And one of the effects you see from response theory, going back to the part A, is that the radius of expansion, that epsilon of the response theory, will go to 0. So this is a nice thing. And note that this can be detected from the time series of my unperturbed system. So my system, I change a parameter, my system becomes slower in the correlating, and I flag how close I am to a transition. That's a classical method used in many applications. But unfortunately, there is another mathematical mechanism which is totally different and separated, which has to do with another property. So this is a property of the attractor. When I am here in this point. Now, in general, a separate quality is not only if something is an attractor. The other thing is how much does the attractor attract? Okay, that's a different property. So another way by which you detect the loss of stability is by studying how rapidly the attractor attracts objects in its, or how efficient it attracts orbit in its near it. So it's a property of the neighborhood of the attractor. So these are two ways, and if this attractivity is lost, you go through a critical transition. But these two mechanisms, again, one is on the attractor, one is near the attractor. These two things are very different. And very importantly, this way to get to a critical transition cannot be flagged by the dynamics on the attractor. So again, there is an essential difference between what happens in the unperturbed case and if I force. Okay? So again, keep your eyes open when people say that everything can be computed from the properties of the unperturbed system. Is not in general true. Can be true or can be not true. Now, let's go to the end, and eventually we go into these critical transitions. And I want to focus on that was actually going back to the beginning. So I didn't study collision of planets, but I was very interested in studying what is considered one of probably the most important critical transition in our planet, related to the existence of multi-stability between, given the present astronomical parameters, between this state of the planet and the ice-covered state, so-called snowball state. And it's interesting story is that the bistability was discovered when people were looking into the possible side effects of a nuclear winter. And that's a nice story. And in the late 60s, Budico and Sellers, that as you can guess belong to different parts of the geopolitical blocks, came to the same conclusion that, well, if we stop for too long the solar radiation from incoming, we could go to a global glaciation, which will exterminate life on Earth. Nice. And in the 70s, Michael Gill proposed a more accurate analysis of these properties, and many people thought this was basically one of those things the theoreticians do. And in fact, then they discovered that this had happened on our planet, that we had been in that state, and this wiped out a few times, about 700 million years ago, almost wiped out entire life. So each time you have an event like this, it's like life has to come back from zero, so you have different forms of life. Maybe you have 3 legs and 15 eyes or something like that. That's fun. Could be a nice experiment. And remember, so we have to beware of this critical transition. So what is the physics of this transition? So we have a negative and a positive feedback. The transition takes place when the positive feedback is stronger than the negative feedback. The negative feedback is the so-called Boltzmann feedback. If an object becomes warm, it emits more radiation, and this is a negative feedback. And the positive feedback is the so-called ice albedo feedback. If the planet becomes colder, it's more likely that it will have more water in solid form. This water will reflect more light. Ice is white, as you can see outside experimentally, and you can get sunburned for similar reasons. And as a result, this will increase the anomaly. Okay, so that's a positive feedback. The transition physically takes place when this feedback dominates over the other. So I will skip on this, and I will just say it has to. And I just want to say that a fundamentally robust feature we found from a zero-dimensional model to GCM, very, very accurate GCM, is the following. There is a region in the solar irradiance, in a range of values in the solar irradiance, where we have bistability between the snowball and the warm state. So this is a very robust feature that has to do essentially by the relevance of the feedbacks you described. So this is the tipping point. So if I'm here and I increase the aerosols in the atmosphere, and then I go here, and then if I want to go back to my relationship, warm life, and it's cold, you have to increase a lot the solar irradiance, and then you can jump up there again. Okay? So I want just to say that you can construct with a simple model, a one-dimensional model, how these states look like. So always the blue is the cold state, the red is the warm state, and this is the state in between, because between these two states there is something unstable, which you have to think it's like the saddle, the ridge between the two minima in the potential. So we will go there, and we see that in the case of this simple model, one-dimensional model, we have that this is the meridional profile of temperature. This is in sine for the cold state, for the warm state, and this is the so-called edge state, which stays in between. And this it's something a bit. It has features which are a bit different from the other thing. Now let's go to where the very interesting part is. So now we have learned that bistability has to do with feedbacks, there are, say, two stable states, and we want to find what is in between. That's the most interesting thing, okay? And if we put noise, we can jump from one state to the other. And so if we jump, we have to say through what we jump. How do we go from one to the other, okay? So now, in the 80s, Grboggi, Ott, and York made in a series of papers that actually are relevant for, they were candidate to the Nobel Prize last year, they constructed this object. So this is the typical bistable regime. As I said, you have a you have a fixed point, another fixed point, and an unstable fixed point in between. That's what I've told you up till now. And they studied the case like this, where I have an attractor, I have another attractor, so it means that there must be a boundary between the two basins of attraction. And then, is there something in between this object, where in between has to be defined? This in between is exactly the place through which we jump. If I'm here, I put an ephemeral noise, and so I will jump here. And what is the place where with very high probability I will cross? Okay? That's this in between, the lowest point in an alpine pass, or in an energy landscape. Or here, it's called the edge state. And that's the one we have seen before. So when I talk about this edge state, this is also the state through which we jump with noise-induced transition that I guess Freddy will also talk about. Now, this edge state, why does it exist? Assume I have a dynamics which is contractive in the phase space, which is always the case, basically. Otherwise, the system will explode. And assume I start my trajectory in the basin boundary. If I'm in the basin boundary, this is an invariant set, so I cannot go here or there, or it wouldn't be the basin boundary. So I have to go somewhere. If the dynamics is contractive, I will converge to a relative attractor. So this is actually a repeller. So it's a thing that is not stable. It doesn't attract, because there is an unstable direction pushing this way. But if I am on the basin boundary, it attracts. So it's an attractor in the limited world of the basin boundary. And that's exactly our important point. So now, let's go back to climate. So this is an image, a 2D phase diagram of climate, of the climate constructed, again, with Plasin. That's a PhD thesis of Robert Boschi. So here we have the warm state. Yes, please. Because, as I said, if you want to understand how you go, I mean, there can be various things. One is, I want to see what is the dangerous. So if you push me towards that state, I am at risk, okay? Second, this is the way through which I jump. So this is the deterministic framework over which the stochastic dynamics of jump sits, okay? So this is the elevator to jump on the other side, okay? That's why it's important, okay? So now, in other terms, this is the projection in 2D, in 1D, for two-parameter exploration of the full dynamics of climate. So I know that for a combination of CO2 and solar constant, say here, I have two states. Can I construct this? And remember that here we see the region where differentiability of the measure, where we have non-differentiability, and then we have this. So these pictures put together a lot of things. So we started with this paper, where we studied the Gill model. And then in this just recently published paper, we constructed, for the first time, the edge state. This edge state had been studied in few dimensions. And here we constructed it in 10 to the 5 dimensions. Okay? So we showed that this object is real. This object has climate relevance and can be practically constructed, okay? And we did the climatology also of this object. We borrowed ideas from previous work done by Bruno Eckert, who had constructed a similar object for turbulent flows, which are quasi-bistable. But the mathematics is a bit different. So what we did is first we constructed a new simple climate model, which has has a coupling of a spectral atmosphere. Still, it has 10 to the 4, a bit maybe 10 to the 4 degrees of freedom, but not much less, because we have a spectral, the primitive equation atmosphere with very complex dynamics, coupled to a simple diffusive ocean, which is nothing but the Gill model itself. Please, yeah, 5 minutes, yes. Now, the question is, how do I find this edge state which is unstable? And we do it through a simple bisection procedure. So how do? You assume all the points here are attracted to the warm state, all the points here are attracted to the cold state. So now, by bisection, you can try into two initial trajectories as close as you want, that basically, such that one goes here and one goes there. So you find a first point at the boundary, in the limit at the boundary. Now, you do the following. It's very simple. As simple as it looks, it does work. Now I am in this initial point, and I started trajectories. They will diverge, because these will get ice albedo feedback dominated by I want to go cold. This wants to go to, to aiguille de midi, and this guy instead will be dominated by the ice albedo feedback, pushing it to Nice, as an example. We have illustrious people here from Nice. But you castrate these almost immediately, you frustrate, and you repeat the bisection, and so on, with the precision you want. So you construct what is called a shadow trajectory in between, which is a trajectory on the basin boundary. So you control the instability due to the ice albedo feedback. How does this basin boundary look like? I showed it as a here. You would think it's a codimension 1 object. After that would be the obvious thing to guess. So there is many dimensions. There is something with dimension -1, which separates the two basin boundary. But mathematics is problematic. And what we discovered, to our greatest surprise, is that this basin boundary is not a manifold, but is a very complex fractal object. So, at all practical purposes, there is not a separation. There is not a manifold separating these two basins of attraction. There is a huge gray region over which I have no predictability. So, this is moving, or these two let's take these two initial points separated by 0.5 degrees at the globally average surface temperature. This is quite close. Now I take 1000 initial condition between these 2 points. Okay? So they are separated by 5 10 to the -4 degrees. And then I say, I plot 1 if they go to the warm state, and I plot 0 if they go to the cold state. So we don't have what is called the predictability of the second time in this regime. And interestingly, maths tell us exactly why we get this. The existence of this fractal boundary has to do with the fact that the time scale of instability in the edge state, so the edge state will be chaotic, as we will see in a second. It will have weather, it will have cyclones, it will have cutoff cyclones, is much faster, because this is some days, with respect to the time scale of the ice albedo feedback, which is it's a climatic time scale of 1 year, few years. The fact that the weather is faster than the climate creates this very complex structure that before had been found only in something like 2 degrees of freedom. So this is really surprisingly robust. And now I give you the phase space, the phase diagram of this object. So this is the warm state. This is the cold state. Mu is the relative solar constant. This is the cold state. And here it's this Melancholia state, which are chaotic. And something to keep in mind for general concept here, in the cold and warm state, we have that if I increase the solar constant, the temperature goes up. Okay? In the Melancholia state, if I increase the solar constant, the temperature goes down. So this is, it can be interpreted as having a negative heat capacity, which is one of the criteria for thermodynamic, for lack of thermodynamic stability. In similar results, Eckert found that if you increase the pressure, the momentum goes down, and this is negative viscosity, which is also a sign of lack of mechanical stability. Let's see how these objects look like. So these are three trajectories initiated very nearby. This one will go to the edge state, cold state, and warm state. At the beginning, you see that we have quite interesting dynamics everywhere. And I will just go a bit. Yeah. So now, this thing is going towards the cold state. And as I will not tell why, but if you go towards an ice-covered planet, you also decrease the meridional temperature gradient, and you have a weaker baroclinicity and weaker dynamics. This guy starts to go towards a warm state, which is closer to, say, present climate. And the edge state stays as it is. And what you see, and that's the fascinating thing, that this edge state has weather instability. So we have been able to separate weather instability from climate instability, but not through timescale separation, but through dynamical separation of the two, through this procedure. I will skip this because it's not relevant, but just to mention that you can have very complex bifurcation, and this edge state, as an example, can have a symmetry break and develop regions which look like a chimera state. I don't know if you've heard about this thing. Regions where it looks like a warm climate and regions where it looks like a cold climate, one next to each other, and having huge instabilities in between. So it's a mix of these states. And eventually, the funny thing is that in a certain parametric region, you find the third climate. So, in fact, there is not just this warm and the snowball climate. In some regions, there is a third climate, which looks like an edge state, but it's now a small climate with a very small basin of attraction. So again, there can be climate surprises as also as of what climate is. Okay? So, conclusion is that we can treat the problem of climate response to forcing through various methods of statistical mechanics and dynamical system theory and bring together what is the smooth response, reasons of high sensitivity, relate this to loss of of time of the correlation of the system, and eventually treat the problem of multi-stability. And in so doing, we can understand what are the gates for the transitions. It's interesting that these very exotic non-climates can be constructed. They exist, they are real. Okay? They are real, and they are, in this very high-dimensional space, the little hole, or let's say the thinnest wall separating the two or more attractors. Of course, if the system has more than two stable states, these objects will become much more interesting. Okay, and remember to beware critical transitions. Thank you very much. Yeah. Boom. Yes. Yes. No, be more specific. Sorry, it's not clear. The question.
So, like, I think you had like 2 bullet points on one slide,
Mm.
and for the lower one, you said that it doesn't really like predict. You cannot predict it based on the dynamics, dynamics.
I think you mean. Was it? Let me see if it this a bit before this. No. Procedure is not robust. Now what? I don't think I said. But I, no. Yeah. Try to say it's important. It's fine.
Well, I guess
It's not an exhibition of you don't have to look cool. We want to try to understand. There's no problem.
So I was just wondering.
Mm.
So if the predictability there's a possibility that it won't be based on dynamics. The transition between two phases may not be able to be represented by GCMs.
No, what you can say is there can be a region in the phase space where you have extremely low predictability, and you can think that these regions of the phase space can be very far from the typical climates, but can be very relevant. Okay, I can say this. Assume I want to I have a representation it's if my model works well near the attractors, but doesn't work well far from the attractors, I might have a misrepresentation of the transitions between the two. That's, as an example, is a problem if I have things which are heavily parameterized, because that's so in that case the system might work well here, might work well there, because I have tuned my parameterization here, but in between, where I usually never go, it might not work, and then it might misrepresent the transition. Actually, that's a very important point. So you see, there was yours. Yeah, yeah, please. The idea is that it should be, if I mean, that's something, it's an open question I would like to understand. I mean, for sure the instant will go through that point. Open question is, do the properties of the edge state reflect, is there a clear relationship between the geometric and dynamical property of the edge state, which is a purely deterministic object? How does will they appear in the properties of the instant when I add the noise? This I do not know. Okay, so yeah, Tapio, I think that was. Okay, yeah, I've been overruled. Yes, please. Yeah, yeah, this. Yeah. Yes, the problem is that it works like this. Assume you have a time series, empirical time series, where you have two peaks in the PDFs. Okay, if you have this time series and you take this peak of the PDF, you can construct a dynamics of this form such that the PDF is the one you have. But this procedure amounts to having this PDF is constructed by observing one observable of a system which is maybe extremely complex, okay? Then you construct the reduced dynamics projected in this unique dimension. The problem is, in doing this, you have a relationship between the statistics and the dynamics, but it's not unique. And it's not robust to perturbation. So this system is like a simulator, but it has no predictive power in general because of non-uniqueness. Yes. Hmm? Which one? No, the edge state in that case, that is not. This model doesn't have seasonal cycle and is autonomous. The question is that actually this is something that Tamash himself would like to study. I think it will survive the seasonal cycle in the sense that you might construct something that moves, that shifts. So you could be able to construct a time-dependent object. You might, but I do not. It's yeah, but the question is that you would control this. The problem is that with the bisection procedure, the being kicked out is not the problem. It's the rest of the dynamics. So I think you could do it. It would require a time-dependent control, which I don't think it's impossible, but it's not trivial, not at all. Yes. Mm. Mm. Okay, I tell you, yeah, it's actually a very good question. Uh, in general, it will not work if the forcing projects on the stable manifold, and orography does. One could interpret the result, it's a very good idea, as the following. Why does orography make such a mess? Because it does this kind of projection and creates strange responses compared to the nature of variability. So actually this might explain why orography, might explain is a big word, might hint at why orography is so difficult, is so problematic. Actually, this is a very good point. Okay, thanks. Yeah, but this is true around a turbulent state. No, but the question is, you see this. I mean, I'm not. You can even as an example, you find similar waves, this to this, also doing the linearization around the background state. So in other terms, it's true that in this case, the linear operator tells you in the around linearized around the mean state gives you already a good answer. But the reason why this works is because you have these geometrical properties on the turbulent state here. Yeah.